Hello, in this lesson, we're going to talk about continuous function at a point. And how is a function is continuous at a point is defined. Okay, so first of all, let's look at the definition. The definition says, okay, I'm quoting the book. Okay, the definition of a continuous function at a point, at a number, is just this box. And I copied and put it here in our flashcard. And what does it imply? It actually implies three items. Okay. So let me put the definition right here. Definition. Okay. A function is continuous at a number A, which is the input. Remember A, if, okay, the limit as x approaching A and f of x is equals to f of A. This implies three items. The first item is f is defined at A. F is defined at A. Okay, i.e. that A is in the domain of the function. In the domain of F. Secondly, okay, the limit exists. And thirdly, is that the existing limit at point A is exactly the same as the function's value at A. So there are three items, must all be satisfied. If all three are satisfied, then we say the function is continuous at a number A. Okay, just remember x is input, A is input, x approaching A, the output f of x approaching the output of f of A. Now, I'd like you to have a comparison. The comparison I'd like you to see is that how limit is defined. Limit is defined, okay? Limit is defined right here, intuitive definition of limit, right? Suppose f of x is defined when x is near the number A. Okay, this means that f is defined on some open interval that contains A, except possibly at A itself. Okay, so I'm going to copy and let me see if I can copy and paste. So if you put this side by side, compare, it doesn't copy very well. Okay, so in the definition of limit, okay, compare with the definition of limit. Okay, the definition of limit, when x is approaching A, f of x is equal to L if such a limit exists. Okay, this is the intuitive definition limit. And what do we need? We need that suppose f of x is defined near A. And what does it mean? It doesn't have to be defined at A. Okay, f is defined near A, meaning that it is defined on an open interval. Okay, it is i.e., okay, so probably, so let me just write type up. Probably possibly, or possibly at A itself, possibly, except possibly, except possibly at A. At A. Okay, you can compare these two definitions. You can see, right? Having limit exists. It's just one of the conditions for a function to be continuous. So if a function can be continuous at A, then we need two more conditions. And what are these two more conditions? One, it has to be defined at A. Number two, the limit must be the same as the function's value at A. So we can say, okay, so we can say the following. If, okay, if f is defined, f is continuous at A, okay, if f is continuous at A, then the limit exists. Okay, that seems the most natural, right? Because if it is continuous, all three must be satisfied, and one of them is in this. And the other perspective is that recall, okay, if it's a continuous, okay, if it's a continuous, recall that we have learned another theorem is that the function, if the limit exists, what does that imply? If and only if. Okay, so I'm going to show you that right here. The limit from left and the limit from right are both exist and are the same. Okay, so limit from left, okay, and limit from right, they both exist and they're the same. And they're the same, right? And of course, the third condition will say that these two would be equals to f of A. Okay, so making all of these connections, let's talk about what it means that a function is discontinuous at A. Opposite. Discontinuous at A, not continuous at A. To be continuous at A, right? To be continuous at A, all three conditions must be satisfied. So discontinuous at A means what? A and B and C, okay? So let me put it this way. Continuous at A, meaning that A and B and C are all satisfied. And the opposite, what is the opposite of A and B and C? If the opposite, we use a notation, there's a bar on top of it, which is not, right? Which is the opposite of continuous. And that would be that not A or not B or not C. What does that mean? Meaning that if one of the three conditions, meaning if one of the conditions, one of A, B, C, one of A, B, C is not true, then the function is discontinuous. Okay, so not continuous, we just have to say if we see one of the conditions is not satisfied, then the function is discontinuous at the point. Okay, and because B also implied, and this other condition, which also has three conditions, you can see the situation gets more complicated, i.e. that if these two both exist and they're not the same, and the limit does not exist, because we know that the limit does not exist could show up in different ways, right? Or the limit exists, but not the same as function. So there are many, many cases of discontinuous situation. Okay, so let's look at some examples. Okay, I look at the homework. Okay, the first question on homework, we have this picture. So let's look at this situation. Okay, this picture. Look at this picture. Okay, this is the first example. Continuous and discontinuous. Okay, so we have the definition right here. Okay, continuous function. Let's see, do we have the continuous function definition, right? Well, we have the continuous function definition right here. We know that it implies three situations, three cases. Okay, and we have all these limit properties that we have covered right here. Okay, let's look at the first example right here. Right, if you look at the points, right? Look at some points that is pretty, it's like this one, right? This point would be a continuous. Why? Limit from left and limit from right is the same, right? The function is defined at this point. So when we check a continuity, we will check these three conditions in that order. Why? The first one is the easiest to check. If you look at the point here, right? This is the point, right? This is the star. And the star is defined. And the limit is, you can just plug in. And it's continuous. It's continuous at this point. Okay, so it's continuous at all these points. Okay, but how about at 1? At 1, it is not, because the function is not defined at 1. Got it? Now, the function, so we're going to make the statement this way. If a function is not defined at, it's not a continuous at 1, okay, at 1, because I'm going to use that symbol. I think you guys might like it. Okay, because I think it's right here. Because, right? Because f is not defined at 1. That's it. It's done. Right? So it is not defined at 1, even though the limit from left and limit from right, they both exist, but it's not defined at 1. The first condition is not satisfied. So let's look at another point, 3, right? So this is at 1, a equals to 1. Let's look at a equals to 3. At a equals to 3, the function is defined as 3. F, right? If we check the first condition, function is defined at 3. How do I know? Because there's a dot, right? So if I draw a horizontal line, if I draw a vertical line, and it passes the curve at exactly 1 point right here. So f of 3 is defined. So a function is defined as 3. Okay, so the first condition is checked. Second condition, however, you can see the limit from left. Okay, the limit of the function from left. Okay, we want to use the proper notation. Okay, we want to use the proper notation. So limit of the function when x is approaching 3 from smaller than 3, f of x is not the same. Okay, it's not the same because when we look for the limit from approaching 3 from smaller than 3. Oh, wait, sorry. This should not be here. So let me invite. Okay. Approaching 3 from smaller than 3 versus approaching 3 from greater than 3, right? These two limits, right? This limit, the first one limit is here, and the other one limit is approaching from right. We'll change it to positive sign. They are not the same. So these two limits are not the same, and thus the limit of the function at 3 does not exist. Limit of the function when x is approaching 3, f of x does not exist. Does not exist. One of the conditions is not satisfied, and thus, therefore, f of x is not continuous at 3. When we say a function is continuous, we must mention where. We must mention where. Okay? We must mention where. If you leave this out, right? If you say f of x is not continuous and leave out at 3, and that sentence is incomplete. And because you didn't mention where, and you're making a general statement, f of x is not continuous, that's not true because f of x is continuous somewhere and continuous somewhere else, and discontinuous somewhere else, right? It's not completely continuous, discontinuous everywhere. Therefore, this statement will be deemed incorrect. You must mention where it is not continuous or discontinuous. Okay, the third case at 5, okay, at 5, okay, at a equals to 5. Well, a equals to 5, obviously, f is defined at 5, right? If we draw a vertical line, crosses 5, it crosses this point. So f of 5 exists, is defined. That's good. However, it looks like the limit, right? the limit when x is approaching 5 from left, and the limit when x is approaching 5 from larger than 5, they both exist and are the same. Okay, so the limit, okay, approaching 5 from smaller than 5 is the same as the limit of the function when x is approaching 5 from larger than 5. They both exist, right? Thus, the limit exists. Limit at 5 exists. Okay? So if we look at the conditions checked, right? It's defined, limit exists, but the third one is not satisfied. The third one is not satisfied. Okay, the third one is not satisfied. Therefore, it is discontinuous at 5. It is discontinuous at 5. Okay, so then you're gonna say, so the limit exists, you check the first condition is true, second condition is true, but the third condition, right? You can obviously see this limit, even though it exists, it is not the same as the function's value at 5. Then you can say, thus, f of x is not continuous. Oops. Is not continuous at 5. Okay, so when you say, well, you can also say f of x is discontinuous at 5, right? So the third condition is not satisfied. So we have, usually if you just mention one of the condition is not satisfied and you demonstrate it properly, and that will be sufficient. Once again, let's look at the logic, right? Continuous, we have to have A and B and C. Not continuous, we just have to have one of the A, B, C is not true, then it is discontinuous. So let's look at another function. Let's look at another function. Okay, this is in your homework. So example number 2. Example number 2, we have a function. Okay, and this function is x squared minus x minus 2 over x minus 2. Is it continuous at 2? Well, it is continuous actually everywhere else. It's continuous everywhere else except at 2. Why? Okay. Now let's first just look at 2. Okay, we're going to talk about other theorems that again that guarantee the discontinuity of this function. The domain of this function is x cannot be 2. Okay, so 2 is not in the domain. So the first condition is what? First condition is not satisfied. The first condition is not satisfied. The domain does not include 2, so this function is not continuous at 2. So f of x equal this particular function, okay, is not continuous at 2. We need to check other conditions. No, there's no need. Okay, it's not defined at 2, thus it is not continuous at 2. Okay, the function is not continuous at 2. If you want to say a reason, because because f is not defined at 2. Okay, so it's very straightforward. That's very straightforward. So let's look at what other interesting properties we have. Okay, what else other interesting properties we have about a continuous function? Okay, the next one is continuous from the right of a number or continuous from a left of the number. Sometimes we are interested in the continuity from the left of the number. Okay, so here's the definition. So a function f is continuous from the right of a number a. What does that mean? If the limit of the function when x is approaching a from larger than a, that's continuous from the right, continuous from the right of a number. Okay, let me put an underline right here. If the limit of the function from the left is the same as the value of the function at a. Okay, and a function and f is continuous from the left of a number a, of course, right? If we change left to right, right to left, then the required situation would be this will be from smaller than a. So this is continuous from left or continuous from right. Continuous from left or continuous from left. Now, the next definition, okay, we're getting a whole bunch of how do we define function defined at an interval? Okay, our previous definition is about function defined at a point. What does it mean that if we say a function is continuous on an interval? Okay, a function is defined, it is continuous on an interval. What does that mean? Well, in this case, we have multiple cases. Okay, so the first case, I'm going to make some columns. F is continuous on an interval, and the interval is oh no. A function is continuous on an interval, so I'm going to make it this way, on an interval. Okay, there are different kinds of interval on an interval. Okay, the interval could be a comma b closed. Okay, a comma b open. Thirdly, these are two rows, a comma b closed and a comma b open. This is called a closed interval. What does that mean? If we say a function is continuous on an interval. If a function is continuous on a closed interval, meaning that it is continuous, okay? F is continuous. You know what? I'm going to reverse this. Okay, I'm gonna put this one over here, and I will bring this one down under. Okay, so in this case, if a function is continuous on this open interval, you can see that A and B themselves are not included. Okay, so a function is continuous. Okay, I'm going to put the word. The function is continuous on every point. Okay, on every point, A less than X less than B. On every point, okay? Any number larger than A and smaller than B is continuous on every point X. Every point X. And X is inside. X is inside. Okay. Now, how about we have this one, right? It's continuous on half open interval. On the one side, on the A side includes A, on the B side does not include B. Well, this is also true. Okay, this is also true. On this case, it is also true. On this case, it's also true. So all of these cases include every point inside is continuous. However, we have some additional. Okay, we have some additional. On this one, because A is, okay, F is continuous on A from the right. So what it means is that, okay, this is also true. That's also true. So not only this piece, okay, when X is approaching A from larger than A, the limit is the same as the function's value at A. How about B? B would be the limit from the left. Okay, is continuous from left, but this is on B. And that's F of B. All right. And the last one that F is continuous on every point, right? They all have all of these. And we have additional, we have this piece and the other piece. And the other piece. So now this is the complete fourth situation of continuity on interval. I hope that's clear to you. In the first case, it's just that. Continuous on an open interval. Continuous on half open interval. And there's a continuity from the right. And there's a continuity from the left if B is included. And there's a continuity on a closed interval that includes not only this piece and also two other cases. So 1, 2, 3. And this one has 1, 2, 1, 2, just 1. Okay, I hope that's clear to you. Okay. So that's about continuity. And we have some other interesting properties. And I think the table, if I think this is fine. This is fine. I'm thinking of changing it to be vertically, so that way we can see them. We can, let's see if I can try it to get it done quickly. Okay, you can reorganize. The reason I want to reorganize it is because of the it was a presentation. Okay, so these presentation, let me see if I can have a different version of it, so that way So all of these has this condition involved, right? So that's for all of them. And that's for all of them. And that's yeah, that it's not going to work very well because it's going to be too wide. I think this is just fine. Okay. Let's see, we have what else other properties there, there could be, right? We just talk about it and we didn't elaborate. This is definition on intervals, right? We just did that. Oh, these are interesting properties. This is called theorem number 4. Theorem number 4. Okay. If two functions are continuous at a point A, right? So theorem number 4. Theorem number 4, we're going to use this number because your homework has these same numbering system. If F and G, okay, are continuous at A, okay, and C is just a constant. C is a constant. Then what? Okay, don't forget this is the premise, right? Both functions must be continuous at the same point. And then the sum, the difference, a constant multiplied the function f times g, f divided by g, except, unless, except the case the denominator equals to 0, right? We're not going to include that case, that the sum, difference, all of these, right? So f plus minus g, f times g, f divided by g, right? Except g of a cannot be 0. Okay. And a constant multiply f are continuous. They're all continuous. And what is more, the next one is also very exciting. Okay, any polynomial is continuous everywhere. Any rational function is continuous wherever it is defined. It is continuous in its domain. Okay, so theorem number 5 is very exciting. Theorem number 5, right? Polynomial is continuous everywhere. Rational function is continuous in its domain. And the next one, okay, 5 and 7, they're the same things. 5 includes 7, right? And theorem number 7, right? So these two theorems basically tell us polynomial, okay, polynomial, rational functions, root functions, trig functions, okay, inverse trig functions, exponential functions, and logarithm functions. Are continuous on their domain. This is great news. This is great news. Why? Because when we were talking about that example, right? F of x equals x squared minus x minus 2. The only number that cannot be in the domain is 2, and it's not a continuous at 2. No problem. No problem. It's continuous everywhere else except at 2. Except at 2. Furthermore, we like to elaborate more on this function. Okay, some of the continuities can be removed. Okay, we call it removable continuity. So look at this function here, right? We look at the limits. Okay, so we first look at, because 2 is the only point that is, 2 is not in the domain. So when x equals to 2, when we look at the limits, we have limit when x is approaching 2, right? F of x. If we try to work out the limits, right? You guys probably would take no time to get this done. Okay, so in order to get this limit, to find out the limit, we're going to factor the numerator. When we factor the numerator, we get x minus 2 multiply x plus 1. And x minus 2 and x minus 2 will reduce, because when x is approaching 2, x is not going to be 2, because x is not 2, so x minus 2 will reduce with the x minus 2 on the top. So we're left with x plus 1. And x plus 1 is a polynomial. So when the limit can be found by direct substitution. So that's going to be 2 plus 1 equals to 3. Right? So the limit exists. Okay, the limit exists. Let's go back to the definition of function. So it's a continuous function here. Right here, right? So the limit exists. The limit exists. The only problem is that f is not defined at 2. But how about we define a new function? How about we define a new function? Okay, so we're going to create a new function. And this new function can be like this. Okay, I'm going to call the new function g. G, right? G function. And this function is defined in the following way. Okay, for x is not equals to 2, x is not equals to 2. For x equals to 2, okay, I'm going to put if there. If there, okay, for x equals to 2, I'm going to take the limit, which is 3, and that will be assigned to the value to the function at 3. This new function is a continuous at. This new function g is a continuous at 2. So now g is continuous everywhere, including 2, right? Rational function. The only problematic point is 2. Now we have removed that discontinuity. So this kind of situation is called removable discontinuity. Removable discontinuity. Discontinuous Discontinuity. It looks right to me. Okay, so let me, okay. I have removed that point that was discontinuous. Now the new function is continuous at 2. Okay. Let's look at some other situation that you can apply the, you can apply the definition, and you can apply all of these theorems. Okay, take another example, such as number 4 in the homework, right? Number 4 in the homework. Number 4 in the homework says, okay, so I'm going to make it example number 3. Okay, it says, find the limit. And here's the limit we're looking for. Limit as x approaching -2, right? And we have a function which is x raised to the power 3 plus 2x squared. This is a rational function. -1 in the denominator is 5 minus 3x. 5 minus 3x. Right, according to the theorem. Right, according to the theorem. Theorem number 7. This rational function is defined everywhere except the number that make it 0, right? And it is continuous everywhere in the domain. So let's see what is the domain for this function. The domain, as long as 5 minus 3x is not 0, that's the only number of concern. That number cannot be in the domain. Okay, so x cannot be equals to 5/3. Okay, that's the only number that's cannot be in the domain. It's -2 in the domain. Yes, -2 is in the domain. -2 is in the domain of the function that we know of here. Okay, and then we can apply theorem number 7, or you can also apply theorem number 5, right? And this function, this function is what? It's continuous at what? At -2. If it's continuous at -2, when we take limit, it's just direct substitution. That's basically what the definition of the continuity says, right? All we have to do is just substitute x by -2. No hustle at all. No hustle at all. And x is replaced by -2. And then you just reduce this number, right? And you're gonna follow the order of operation. 2 to the power -3, that's -8, right? And wait a minute, I think I missed the parentheses here. Okay, 2 times -2 squared. So -2 squared is a +4. 4 times 2 is a +8. And -1. Denominator is 5 plus 6, that's 11. So in the end, we have the -1/11. I hope I didn't do anything wrong. Okay, you may like to pause and check the word. I double check, it looks like it works. It works, right? You can see in the case that we know the function is continuous at a point, It's just to find the limit at the point. It's just a simple substitution. Okay, direct substitution. And there are some homework problems that we have covered in class, and I'll leave some of them for you. And let's look at example number 4. Okay, and this one is question numbers. This one is also in your homework. Okay, it asks us to evaluate this limit. This limit when x is approaching 1. Okay, and we have an interesting expression. 1 minus root x over here is 1 minus x, and there's an arc sign like that. Okay. To tackle this question, I wish to introduce to you the next theorem. Okay, the next theorem. The next theorem is about composition of function. Okay, so this is theorem number 9. This is the application of theorem number 9. Theorem number 9, let's see what it says. Okay, so we're gonna, the premises actually, okay, G is continuous at A. G is continuous at A. Okay, that's the first condition. Second condition is F is continuous at G of A. F is continuous at G of A. You may wonder, why is that, right? So I'm going to explain to you. Wait a second, I think I'm quoting the wrong one. Oh, this one, sorry, theorem number 8. Sorry about that. Okay, we don't need, we will get to the next one, but this one is theorem number 8. I'm sorry, I skipped this one. F is continuous at B. Okay, F is continuous at B. F is continuous at B. Okay, the first condition. Second condition, okay, F is continuous at B, and the second one is there's a limit. There's a limit as x approaching A, G of x equals to B. Okay, G of x equals to B. You could actually make this number 2 and this number 1. Okay, then the limit of when x is approaching A, F composite G of x is equals to F of B, i.e., if we know that B is this limit, we can write it down as F replace B by its equal. In other words, you can take this limit, goes through F, okay, and put it inside of the parentheses of F for F. What does that mean? What does this mean? Okay, we're gonna show you by example. Okay, example number 4 would be, the example we're going to talk about. But before we do that, look at F composite G. Okay, what is the kind of situation here? Okay, so I'm going to put a note here. These are the not the thing you don't have to show the work here. Is that we have an input. The input is going to give it to G. That produces a G of X. And this G of X is going to be the input for F. Okay, that's what a composition means. So that in turn produces F of G of X. So this is the meaning of F composite G. F composite G. Okay, we know that F composite G is defined as F of G of X. Okay, so that's how the composition works. So the actual process is going from inside, outside, from inside. So the input is given to G, and after G processes it, and the output is going to be the input for F. So that's the process. Okay, so that's the process. So when X is approaching A, okay, when X is approaching A, G of X, okay, G of X is approaching B. That's what we know. This is approaching B. You see? This is approaching B. So B is the limit. So when X is approaching A, G of X is approaching B, so this piece is going to approach what? Okay, so this piece is going to approach right here, F of B. F is a continuous function. In other words, the limit symbol can go across a continuous function. So if you have a limit here, you know F is a F is continuous, and you know G has a limit, right? Continuous and G has a limit, and then you can take this across the F and put it inside. Okay, so now to apply this theorem, we need to check a couple of things in this example. Okay, so we have the theorem right here. So I'm going to show you how we work this out. Okay, so in this situation, our F, the outer layer function, is arcsine. The inner layer, the G, is 1 minus square root of X or 1 minus X, right? So we need to prove that the limit exists. Does this have a limit when X is approaching 1? So the first thing we want to work on is we want to work on this limit. Okay, so if I can give you a simulation, okay, so our F is arcsine X, okay, our G is this piece. Oh, wait, this piece. Sorry, not this one. Okay, so this is F and G. So before we can apply this theorem, before we can apply the conclusion of the theorem, okay, we need to check the first condition. Okay, so when limit X is pushing A, in our case, A is 1. A is 1. So we're going to work on this limit. Okay, replacing ZG by, is equal. Now the question is that when we look at the limit of G, when X is approaching 1, when X is approaching 1, the numerator is 0, numerator approaches 0, denominator approaching 0. We cannot direct substitute. And what can we do? we will be thinking maybe we can do some algebraic manipulation, right? And what algebraic manipulation you might be thinking of? Conjugate, right? See if we can do it. Okay, sometimes we can do it, sometimes we can't. The conjugate of the numerator is 1 plus root x. 1 plus root x. So we multiply by 1. Anything times 1 stay the same, right? And the next line, the numerator on top, numerator times numerator. So we're gonna get, so these two multiplied, right? Numerator times numerator, we get 1 squared minus root x squared. And the denominator, 1 minus x, we're going to insert parentheses if we want to bring them together. Like that. Okay, and the top, if we simplify the top, 1 squared is 1, root x squared is x. X is approaching 1, x is not 1, x getting close and closer and closer to 1, but never is 1. Therefore, 1 minus x is not a 0. So this dynamic process, because 1 minus x is not 0, so we can reduce this on the next step. Okay, so 1 minus x, remove the 1 minus x in the bottom, and we can remove this parentheses. Now we can do direct substitution because this is a rational function, root function, adding, this is the quotient of two functions, and this function is defined at 1. The limit is just a direct substitution. And that direct substitution will give us this number, which is going to be 1 over 1 plus root 1. Okay, this step it can be omitted, and that's 1 over 2. Now it's interesting because we need to be aware of arcsine's domain, right? And arcsine's domain, what's the domain of arcsine? The domain of arcsine is domain of arcsine is the input x must be between -1 and +1. And 1/2 is indeed in the domain. So now, well, theorem number 7 guarantee arcsine is continuous, right? Arcsine is continuous in its domain, right? Arcsine is continuous in its domain. In its domain, which is x is between -1 and +1. So let's see what are the conditions. Have we checked them all? If it's continuous in its domain, it is certainly continuous because 1/2 is in this domain. And so the second condition is that this is a continuous at the point. This theorem does not require continuity on an entire interval. Is it continuous at half? That will be enough. Okay, continuous at x at a equals to half. No, I should call it b. Okay, let's not make it confusing. Okay, I'll give you another version of this solution. Okay, you don't have to explicitly introduce atoms. Okay, so this is the limit b as is stated in the theorem, right? This is the b, which is the limit of g, which is half. And the function arcsine is defined is continuous at b. You see, there's two conditions. There are two conditions, right? So I'm going to copy and paste this theorem. I'm going to put it right under. So we'll verify the condition. The first one we have verified, we found the B is half. And secondly, with that, we found F is continuous at half, right? So both conditions are checked. Therefore, apply theorem number 8, right? Apply theorem number 8, what can we do? Well, we can apply exactly the theorem as exactly the theorem says, right? And A is 1, right? And this is what we're going to put our function in place. That's going to be, this is arc sine of, right? 1 minus root x, 1 minus x, okay? And what does that equal to? Equals f of b. What is f of b? We can remove that part, right? We found this limit is what? This limit is half. This is 1/2. You see, just directly apply the theorem. And that's arc sine half. What is arc sine half? Arc sine half is pi over 6. Okay. If you need to review that trigonometry arc sine, I would let me show you where to find them. Okay. It's in the first week. Okay, it's the first week. Arc sine, domain, range, and graph. Okay, it's right here. All right. All right, so let's come back here. Okay, let's come back here. So then that's theorem number 8. You can see it's rather useful, okay, for composite function. And theorem number 9, is basically if f and g are both continuous, right? G is continuous at A, f is continuous at g of A, so it has even stronger condition than theorem number 8. This is theorem number 8. What is theorem number 9? Let's see, let's compare them. Okay, theorem OREM, theorem number 9. So what are the conditions in theorem number 9? First one, G is continuous at A. G is continuous at A. Right? First one. Second one, F is continuous at, instead of adding B, this one is stronger. Is instead of adding at B, is at G of A. You see, in theorem number 8, it didn't require G is continuous, but this time in theorem number 9, it requires G is continuous at A. And so F is continuous at B, so because that B will become G of A. Okay, and then the conclusion saying that F composite G, okay, F composite G is continuous at A. So what does this say? It is continuous at A. So what does that mean? Okay, two continuous functions, if they are, they make a composite function, the resulting continuous composite function is also continuous. So composition of two continuous functions is continuous at point A. Okay, all right. So this theorem says that. The next one. I think intermediate value theorem is going to be another lesson. It's going to be another lesson. We already covered that in class. And let's see, there's any homework questions. Should I go over about continuity? I think I'll just leave them for you. Okay, let me just double check one more. Homework number 5. Okay, I think this lesson is long enough. Okay, until next time, thank you for watching.